As we saw in the previous two examples, for simple ordinary differential equations, there are sometimes methods that we can use to analytically find solutions for what, in those examples, x of t was. In the first example, the problem was separable, and we were able to use techniques from our differential equations class to solve for x of t. In the second example, we had that it was a second order ordinary differential equation, and we have some methods to solve those analytically as well. And it's very convenient because we can find that closed form solution or that analytic solution for what x of t is. But many times we have ordinary differential equations that are nonlinear, which we barely cover in a differential equations class, or even it might be linear but just more complicated or have complicated right-hand sides that are being applied on it. In that case, we cannot find a closed form or analytic solution to it using any of the methods discussed in undergraduate or even a graduate level differential equations class, because it falls just outside the scope of anything that we've covered, so finding it could be very difficult or maybe even impossible to find that closed form solution. So the solution to this, and also the solution to ones we could solve by hand but maybe don't need, is that we can find a numeric solution to them. So we're not going to get an algebraic expression for what x of t is, but we will be able to get at discrete points what that value is. And it's similar to the type of problem we had in lecture 8 when we were talking about either integration or differentiation. In those types of problems, if we want to find the integral of a function or the derivative of a function, and we didn't have a closed form solution, we could get our numerical approximation to what those values were. And we didn't get that expression, but we could plot it and we could use it pretty well. We can get these numeric solutions using Matlab, but first we have to put our ordinary differential equation into what's called state space form. And that's going to be able to solve it. Now Matlab and most other solvers that you would use are only capable of solving first order ordinary differential equations. So like what we saw in that first example we looked at, but not exactly like what we saw in the second one, because in the second one it was a second order differential equation. We had an x double dot term. In the first example we had an x and an x dot term, which would be a first order ODE. So again, Matlab is restricted. They can only solve first order ordinary differential equations, but it can solve many of them simultaneously, is the advantage that it has. Now fortunately, we can take higher order differential equations and we can write them as a system of first order differential equations, and that's what we call our state space form. So for example, in the second problem that we looked at where we had that x double dot term, we're able to rewrite that as two first order differential equations that Matlab is going to be able to solve. So we need to use state variables to accomplish this. So what we have to look at is what are the independent variables we have in our equation or equations. In the two examples we looked at so far, we only had one dependent variable and their derivatives, and then the one independent variable, time. So what we need to do is we're going to look at our dependent variables and see how many derivatives of it, or what the highest derivative of each of them is, and going to use that to determine which state variables that we need. We're going to rewrite our original equation or equations in terms of these state variables such that they have only one derivative term. And we'll see in the example coming up how this is really accomplished here. And the rule we want to keep here is if we are able to write a term as just a state variable, we must write it that way. And we'll see how we have this choice in the following example. We then want to take those equations that we rewrote and isolate the derivative term. So we want just a derivative term on the left-hand side, and the right-hand side expressed as our state variables and things that are functions only of time. We then need to add any additional mapping equations that we need, and we want to keep track of at the end that we have as many equations as we have state variables. So we'll see that if we have two state variables, we're going to need to be able to write two first order ordinary differential equations in order to solve for those two state variables.